very much. I have a lot of friends here. It's the first time I've ever given a talk at USF, and I am really happy to be here and really realize that there's a lot of people here that I have known for a long time in my career. 1998 on one of the Yonggang cruises, Dr. Hu, and known Bob and Yonggang and former students Roy Ying, and like there's a lot of people here that that I have known over the years and helped me in my own career. So I'm really happy to be here and to talk about a couple of things that are, I hope, of interest to all of you. There's a couple of things that that I'm going to talk about. So the number 2 there is the freshwater fate following Hurricane Harvey, and that's what I was originally going to talk about, but I just can't help myself. I can't help myself. Got to talk about this MASTR experiment that happened in the Yucatan Channel and earlier in this year. It's some of this stuff that I'm going to show here is just like to die for ocean observations. It's really unique data set. I think from the legacy point of view, it's something that we'll be looking at for a very long time. So just to show, so I'm going to say something about GERG. So GERG is the Geochemical Environmental Research Group. I am the director of that now, so I've ascended to my level of incompetence and at the stage of my career where I can direct something. What happened to the 162 cubic kilometers of rainfall that fell during Hurricane Harvey? Talk about that second. And then the MASTR experiment. MASTR is the mini adaptive sampling test run that was part of the NAS Gulf Research Program, UGO's program, and that just came out of the water earlier this year. So talk about that. So words about GERG. So first of all, GERG is a soft money institute. A lot of you know what that means. For the students, it's let's just say we eat what we kill. Right? So we have to go after money, we have to go after funding, we have to find that and come up with research projects. Really, the only hard money that's at GERG is like my teaching salary. Right? So my 9-month report is the only hard money that goes into GERG. There's about 25 employees. That does not include students. Usually there's 10 to 15, sometimes 20 students that work out at GERG. So, and that's the facility there. And you will see that facility at the end of September. It's when you come visit us for the UGO's meeting that's happening. It became a center of excellence. That means something. I don't know if that there's a counterpart to that here at USF, but that means that it was approved by the Board of Regents, We're a state university. That means it became an official thing in 1987. And again, soft money, Graham Road, which means it's about 5 miles south of the main campus. I'm going to say something about the ocean observing part of GERG. GERG has an environmental geochemistry. We have 11 mass specs out there. We do a lot of that kind of work. I'm not going to talk about that other than what I just said. The observing part is funded through national, state, and even global programs. It's observations to inform numerical prediction. We get funding through the Texas General Land Office. That's a lot of our principal funding through the state comes through that. I know there's state money coming through systems here at USF. General Land Office, I'm going to talk about that in a second because that funds our buoy program. We get a lot of NOAA funding, various aspects, various line items within NOAA, National Science Foundation, but NAS, DOE, Navy. Yeah, if you're running a soft money center, you need to have a balanced and diverse portfolio. Right? It's the only way it survives because everything has cycles to it, and you try to ride through cycles best way that you can to keep your funding sustained. So, okay, so, and principal among our work here is buoys and moored systems, autonomous vehicles, and high frequency radar. So we have a lot of things that you have here, and a lot of the things that we have that you have here, I learned from you how to do some of this stuff. So, this is TABS, Texas Automated Buoy System. That's our family of buoys over there on the right. That's the website, tabs.gerd.tamu.edu. Again, General Land Office is the thing that funds that, and you might wonder why does the General Land Office fund things in the ocean? It's because they have oil spill purview. Right, so when there's an oil spill off coastal Texas, they need to put assets in the water or along the beaches to do the mitigation, the cleanup. The information that we provide in real time with the buoy program gives them that information to have informed decisions. It's about $1 million a year we get from the state for the base TABS program. There's about another $1 million per year that funds some of the research and development parts of the buoy program. So there's M&O, maintenance and operations, and then there's R&D parts associated with that too. And I just have to say, it is Texas. I've lived in Texas a long time, not from Texas, but I lived there for a long time. Just saying, in Texas, there is on average an oil spill per day, right? So they use this information every day in Texas to mitigate whatever, and using the definition of a spill is on the order of about a barrel. And so the big spills, which are thousands of barrels, that doesn't happen every year, maybe every few years, but every day they use this information. They do trajectory mapping, they use particle tracking, they do a lot of different work, and they need three-dimensional models of the current and three-dimensional observations of current as well. This is just showing some of the buoys on deployment. In fact, this particular one deployment was at the Flower Garden Banks, where we had 2 buoys for a long time, for about 18 years. In 2018, when there was a lot of deregulation from the federal government, those buoys came out of the water, but they're just sitting at the backyard right now, waiting to go back out. We would love to put them back at the Flower Garden Banks. We also have gliders. Right now we have 5 Slocums. 4 of them are G2s. Where's Chad? Is Chad here? Oh, there you are back there. So 4 G2s and 1 G3 is what we have. We have 2 surface vehicles, 1 liquid robotics wave glider and 1 autonaut. This is the liquid robotics wave glider there, the smart surfboard. I don't show the autonaut, which is more like a smart canoe. That's a deployment. Actually, that's a deployment right after Hurricane Harvey back in 2017. And this is showing our gliders on the back of the RV Manta, which is the 95-foot catamaran out of Galveston that will do 38 knots. And yes, it is that cool to be on the boat. Our radar network, so we have 2 different radar systems that we have. The Texas system has 6 radar that stretch down. So this down here is Fort Mansfield, up to Sabine, so that's the Texas-Louisiana border, and that's the coverage shown there. We also occupy and maintain and service the 2 Mexico sites. I'm going to talk about them a little bit. Down in Quintana Roo, near Cozumel and Cancun. You can see that over there. The data are at that specific website. Right now, the radars are down because Hurricane Beryl came through in July and knocked them down. So we're in the process of putting that in. This one here says Isla Mujeres is currently under construction. Isla Mujeres is right here. It's this little island that's right there. When we get that 3rd radar system in, that'll give us redundancy, and hopefully we're not going to have as many downtime because of things like hurricanes that come through. The 1 radar that's here at the UNAM campus is this one right there. So that's more secure. It's a more stable spot. We don't have nearly much downtime on that location as we do at Isla Contoy, which is up here. And Isla Contoy is a very remote station. It's only gotten there by vessel, by small boat. To get out there, we have to cart all the thousands of pounds of batteries. It's all the batteries are all there, charged by solar. So there's no real power out there. Anyway, that's been installed since June of 2022, and that's part of the story that I'll be showing you. Okay, so let's get into hurricane. So I'm going to start with Hurricane Harvey. So this is Harvey. It made two landfalls. The first was near Rockport, Texas. It came in as a Cat 4, right? That's the end of August of 2017. And then it went inshore, went near Victoria, Texas, which is west of Houston. It spun for a couple of days and then went back offshore near Freeport, Texas, went off along the coast towards the east, and then made the second landfall near Cameron, Louisiana. So in the western part or the eastern part of the shelf, and that was 4 days later. So that's just an image of that. This is showing the long wave rate. Let me start the animation here. Where? That's not. You should start the animation. So I think. Trying to get this to be. Not this. I want this as a laser pointer tool. That's what I want. I mean, this is an animation. It should be given. Right now it's a pointer. I mean, we don't need it to be a pointer. Let's see. Option. Well, that's neat.
Click back on the down further. There's a little pen icon to the left.
Yeah. Oh, that's it. Okay, so that's showing the animation of the long wave radiation, and that's showing the sea surface temperature anomaly, just showing the cold wake behind the storm, showing the track as it comes in into coastal Texas near Rockport, coming in, spinning near Victoria, Texas, then going out again into the Gulf of Mexico near Freeport, Texas, and then coming in for the second landfall near Cameron, Louisiana. Right, so that's just showing that. You can see the cold wake over there. So colder temperatures are in blue, showing that. I think this is working. Oh, thanks. So let's go next here. So there was a lot of suffering, a lot of human suffering that went along with the storm. This picture up here shows the western part of Houston, where flooding was into neighborhoods. There was a lot of fresh water that came in. That right picture is to me, it's the most spectacular picture of this entire sequence, because that is I-10 near Winnie. That's the highway that goes between Houston and New Orleans. That's 30 miles inland. That is not storm surge. That is fresh water. It rained almost 2 meters right at that location. So you're getting white capping on I-10 there. That's all fresh water that rained right there, right? And the thing is, where did all that water go, right? Because that's not inundation and surge. That is flooding from the terrestrial side, and then it has to go back into the ocean. So my job here is to tell you what happened to all that rain, right? Down here, so this is inshore. This is, in fact, this is 150 miles inshore. This is right near my house. This is what was the Texas Speedway in College Station. And there was hundreds of thousands of cars that were destroyed within Houston. You had to put them somewhere. And so they found a lot of places like this. And they went, like my house is just, it's not even a half a mile from here. It's like across the street here. And they just stored them there almost for a full year. Those cars ended up at that location. Where they ended up, ultimately, I have no idea. But lots of impact. At my house specifically, there was about 21 inches of rain. And we are 150 miles inshore. So using the GPM, or the Global Precipitation Measurement Satellite Network, that NASA has up, we're able to measure, get quantification of how much rainfall fell on this area, both on the terrestrial side and the ocean side during this time period, which is, and this is the time period that I'm using here, from 23rd of August, which is before the landfall, through the 1st of September, which is after the storm passed to the north and east, right? So if you do this and you look at this and you come up with that heat map that's over there, and right in where the E is in College Station, that's where Texas A&M is. You can see that there was a lot of rainfall that fell here. And if you total all of that up, you just do a summation of everything that's in that square, you come up with 162 cubic kilometers, right? And to put that in perspective, that's 39 cubic miles, or a 3.4 mile cube, right? So it is a lot of water that fell on this area. And so then what's the fate of that water? And that's what I'll be talking about, right? So so this is total volume, land and sea, 162 cubic kilometers. As my predecessor, the director of GERD, Tony Knapp, said to me the morning of the landfall of this hurricane, they call it a rapid for a reason, right? You have to be fast. Yeah, it's called a rapid. So get your request in for the rapid funding soon. If you wait a week, it's already old news, right? So we wrote the proposal to go back out into the water, because we had just done a cruise, a full shelf survey of the cruise that was funded through the NOAA Restore program. For Texas, no, it's called Texas One Gulf. It's what ours is called. They just funded us a cruise before the storm. We needed to go back out and see what the impact was, right? And we wrote the proposal as it was making landfall. So if you're running right or rapid, you have to be rapid. Where did the rain go? That was our first question. And did the fresh water get to the Flower Garden banks? Because there had already been a mass mortality event at the Flower Garden Banks Coral Reef the previous year, due to a combination of reasons: freshwater intrusion, stratification, and upwelling of low oxygen water. So this is where we had the station. So on the right there is the showing the red is where we had the repeat CTD stations. The yellow and the green were where we had not as much coverage on every one of the cruises, because we had 4 cruises. We had 2 that were before the storm. They went out in June and in August. And then we had one right after the storm in September. And that one I call the Harvey Rapid Response, or HRR, or HER cruise. And then we had another cruise in November of that year, a couple months later. Right, so June, August, September, HRR, November, 5 cross-shelf transects. You can see them in the red over there, and transiting over to the Flower Garden Banks, which is this cyan color over here. And so, and there was real concern that there was not much we can do except monitor for that. Wasn't much mitigation that we could do. This is the hydrant. So this is just TS from the 4 different cruises. So all the data combined and shown on one plot. You can see the seasonal differences here, right? Because y-axis here is temperature, but that's proxy for depth, but it's also temperature. And so by November, things got colder. You can see the green here, which is the November cruise. Things are colder than what they are in the summertime. You can see also in the red and the blue, the stretch to the left here, which is the fresh water, right? So salinity is on the x-axis over here. This is freshwater over here. And you can see that in the summertime, in June, there was a lot of fresh water. But in August, there was not a lot of fresh water. So you can see that in cyan color here. So by then, Texas coastal current, this is as you know, this is the latex paradigm. So Louisiana Texas shelf paradigm from the early 90s. John Cochran, Frank Kelly came up with this paper in the late 1980s, tested in the early 1990s, which is there's two seasons to the Texas coastal current. There's the non-summer season, which is down coast, and there's the summer season, which is up coast. In the summertime, when it's up coast, you have a lot more higher salinity water, and that cyan color is showing that, right? And then the storm happened, so that's the red here, and you can see a lot of fresh water that occurred during the storm, a lot more fresh water. In fact, it looks a lot like what was going on in June, just at the time when there was a lot of fresh water from the Mississippi, but the difference being this time between that cyan and the blue here, that's when the storm happened. So this is, so I like to show this one too, because this is showing the data so it's always good to show the data. This is showing the pressure time series at the time of the storm. So this starts mid-August and it goes till the 1st of September. And you can see that the elephant in the room here is that there's a big dip in the atmospheric pressure at this time. And you can see here, so if the black line here is buoy X, which is right here, this is the TABS buoy X, right? And then and that buoy K, which is green, is here. It's the green line that's over there. This gives you an idea of what the spatial and temporal scales of this storm is as it is moving past these locations. Right. So, and this is not my opinion, it's the data. Here's the data. What is it? It's the data. It's right there. Right. So I do like to show this too, point this out, that the green time series starts on August 24th. And that's because we were having a TABS service cruise at the time that the storm is moving its way from the southern Gulf of Mexico into the northern Gulf of Mexico. And the guys on the cruise put the buoy in the water just hours before it passed that location. And why buoy here is because as soon as they put it in, they're like, we need to get out of here, and we need to do that quickly. So they turned the boat, they started heading back towards Galveston, lost power in the boat, screws turned off. They just pointed the hurricane is now moving in the area and it's going to Cat 3, which means all the ports are closed, right? So they just had to point the bow into the winds and just took it for the next 2 weeks. It took them 2 weeks to come back in. Right. So for me, but we hear it. This is showing the winds from the TABS buoys, and kind of what you're seeing here is, so K and J are down here in the southern part, X is offshore, and here at the elbow, V is far offshore at the Flower Garden banks, and then B like buoy or Brazos, it's near the Brazos River mouth. It's the only river in Texas that actually goes directly through into the Gulf of Mexico before going into an estuary. It's the Brazos River. It's also the river that goes right next to Texas A&M. So it's like our local river upstream. Buoy B is right there. That's where the Brazos River comes out. And what this is showing is, so the first landfall and the second landfall is shown in the colors here, the red and then the blue. And you can see as the storm is moving past these different locations, it's affecting what the wind. And this is, I don't know if there's any atmospheric scientists, they always yell at me for this. This is oceanographic representation, right? Which means this is the direction of which the wind is going towards. It's not the wind direction where it's coming from. It's the oceanographic representation here. And so it's showing that, and you can see how the spiral as the storm, as that cyclone moves through, moves by. You can see how as it moves past these different locations, how you have reversals, right? And all of this is driving what's going on the surface, right? So it's driving the surface currents. I have the next slide's going to show the surface currents. But what I want to point out here is that there's fairly persistent down coast winds that are happening on this time period. That's really important because that's when all the fresh water started entering the Gulf of Mexico as it went through people's yards and over barrier islands and all that. It started going into the Gulf, and that's when it started catching the ride down coast towards Mexico. Right, so that's so just remember that here. This is the currents, and so with this, I've done the alignment. So we've rotated the coordinate system so that every one of these currents now is no longer. So the atmosphere doesn't make much sense to do it this way, but on the coast it does. To say, if you're going down on this plot, that means you're going down coast, right? So along the coast, down towards Mexico, if you're going up coast, and there's the positive numbers, it's going towards Louisiana. If you're pointed to the left on here, it means you're going onshore. If you're pointed to the right on here, it means you're going offshore. And what this is saying is pretty coherent currents pointing down coast in this aftermath, after the storm has already made landfall the second time and moved away. There's mostly currents that are moving down coast, carrying all that fresh water with them. So this is just showing a representation of all the buoys and all the, so that the NEBC buoys are here, the TABS buoys are here, showing the winds and the currents. You can see the storm moved near Victoria, Texas. It sits and spins for a little while, then moves offshore. You can see all the currents and the winds responding to that as it moves offshore. This is the second pass along the shelf, and then moving towards the east, and then up and towards Cameron, Louisiana, to make that second landfall right there, and then all the response to that. So we have a lot of data to show how this is the oceanographic system is impacted and how it's responding to all those winds. The next slide here shows this is time series. So one thing about this is I think of this as we had cruises, shelf cruises, spatial cruises that went out, covered a lot of area. The time series then provides the connective tissue, right? So the strings of time series that connect the two cruises, that the one that happened before and after. In fact, we have it from June all the way to November. So I can look at all of this. I'm concentrating just on the August to September time period. The northern buoys, which in buoys B, R, F, and D, these are these buoys that are out here, show almost immediate response to those winds, to the surface currents, to the fresh water that starts coming out. You can see the timing here as the red, which is buoy R, which is the furthest to the east here, starts showing a dip in the salinity, but it's really right here is when you have a real strong dip in the salinity, right? So, and that happens after buoy B, which is the Brazos River buoy, which is the one that's closer to Galveston, starts showing that there was fresh water coming out onto the shelf. And then you have buoy F, which is just a little bit further offshore. That's when the sequence hits next year. And then at the Flower Garden Banks, the blue line just shows there's almost no impact of that fresh water out there for as long as this time series is going. In fact, we have the whole time series that lasts more than a year. It never made it out. So one of the questions to NSF, did it get out there? The answer is no, never got out there. Why? Because we have the data. Never saw it out there. Down in the south, it's a little bit different here because down in the southern buoys, so this is JKDX. So JKDX down here, you can see that the phasing is a little different. It starts later, and D is the one that's closest to Galveston, and you can see the tick off, the decline, the reduction of salinity is first there, followed by the black J here comes down, and then followed by K, which is the one that's offshore. So we can see that all tick off here, and then the blue line is buoy X, which is further offshore, and it never really got further offshore. So what we're starting to get a picture of is that fresh water is coming down, it's flowing down coast. It's staying mostly coastal. There's a little bit of a curl over here as the fresh water starts hitting J, and there's a little bit offshore with the blue or the red of K. If you want to look at this spatially, so this is just a map of the surface salinity in September at the time of the cruise. You can see the blue here, and I'm using CM Ocean color bars. Is that most of that fresh water is combined to the inner shelf area. That's where the blue is, right? There's about 50 CTD stations that make up this plot. But if we compare that to what was going on in August, you can see that it was very salty in August, right? So this is all the yellows and the very pale blues that are here. That's really showing the Texas coastal current reversals, typical summer pattern. And then once we get here, the question is, can I do the comparison? Can I quantify the comparison? How much fresh water would have to be injected on the shelf to make the three-dimensional pattern go from that to that? The other thing that we have here is, so this picture is looking towards the southeast, right? So I'm standing on the boat, I'm looking towards the southeast, and I'm right at this location. And what I'm seeing is some kind of front. And I will tell you, like, I know my group at GERG, they have measured some nasty stuff over the years. Nobody wanted to get into that stuff and take a sample. Nobody. Like, I'm not putting that in my mass spec. That's not going to happen. So we started radioing it into the state, and then to NOAA, they send out planes and stuff. We have no idea what that was, but it's probably all the stuff coming from people's houses, from the garages, right, from the sewer, like all that stuff. And it made a very strong front, and it's right here, right at this location here, where the front is for the fresh water with some saltier water. And blue here is fresh. So then it became, let's quantify it, right? So things that we use to quantify. So we use Gauss-Markov, optimal interpolation, Gandine from the mid-1960s. That's where you get some of your best mathematics for doing the optimal interpolation. That's how weather maps are created, right? John Wilkin has a really great paper from 2002 on this. In fact, his code is available, and you can look it up. So it's optimal interpolation, objective analysis, and we got estimates for gridded fields for every one of the cruises. And that allowed for our ability to estimate the freshwater volume, and we can then use differencing to come up with numbers for how much freshwater is on the shelf between these different cruises by subtraction. And the equation, I was talking last night to somebody, this is the equation that we used. It's the Blanton and Larry Atkinson equation from 1981, right? And it just shows you the freshwater fraction. You can use that to come up with the volume of freshwater. You use that. So this also has an application. Let's do that. So this is going to rotate a little bit here. So this is just to show that I was able to do this three-dimensionally, and I did this programming. I can't not to do so much programming anymore these days. Too much running stuff, and I don't like aspect of the job. I like to do programming, and so I did program this, and it's in MATLAB, and I know whatever. But it's showing the three-dimensional structure based on the CTD data and the thermoselenograph data, and also the TABS buoy data. So we put as much data into this map as possible and come up with a really good estimate. We have error bars on this too. And after you do that, let's see, let's go here. So let's just, I need to talk you through this. I'll talk you down through this. So this is some of the popular press. This is from the Houston Chronicle. This is Washington Post, but very similar thing that was in the Houston Chronicle. It's showing what does that much fresh water look like as compared to what downtown Houston is looking like. And so I have some numbers on here, and I'm just going to say, so what we did over here. So this, let me just pull you over to this graphic here. This is x-axis is freshwater volume. This is depth. And so what I did was, as a function of depth, because I had all these gridded fields, three-dimensional gridded fields, I was able to say by depth, by slices, how much fresh water was in each slice. And this is by slice. So at 120 meters of one slice, 1 meter thick slice, there was this much fresh water, right? And then the next, and then the next. And you can see here that doesn't take a rocket scientist to say that most of that fresh water was in the upper 20 meters. If I take this graphic and then I integrate it vertically, starting with 0 at the bottom and integrating upwards in the upper 100 meters, right? This is the integration of this line over here. what I end up with is a number that says 67 cubic kilometers must have been injected into that space between the time of our cruise in August and the time of our cruise in September. Right? And what is the thing that was different? That storm. Right? And what this is saying too is a lot of that fresh water, so 67 is the number, a lot of that fresh water is in the upper 20 meters. Put this in perspective, and I've given this talk several times. A lot of people don't believe this number. I'm telling you, this is a true number. Believe me, it's a true number. If you take the average Mississippi outflow, which is 10,000 cubic meters per second, that's what the average Mississippi outflow is. That corresponds, that number 67 corresponds to 36 days of Mississippi River water, the average Mississippi River water injected in that location as a result of that storm. So, and you think about the I-10 Winnie 35 miles inshore graphic, all that water made it out onto the shelf. It impacted the biota, impacted the water quality, impacted virtually everything out there. So let's do the accounting for that. Well, so that's what it looks vertically. This is what it looks like horizontally. So the lighter colors here are where things got pressure between the two cruises, between August and September. And the darker colors here is where things got saltier. So what this is saying, all those light colors are saying, mostly inshore is where that fresh water went, right? Offshore, especially near Flowervine Banks, there's not much change, right? And there are some stripes that go on. Like I did all the optimal interpolations in order to make these maps. There is some striping that goes on here, but I put in this to some covariance and analysis, and that number is good within about 5%. So let's do the accounting. I said before, from the GPM, there's 162 cubic kilometers that fell. I can partition that out to be 44 that fell on the ocean and 118 cubic kilometers that fell on land. So let's move that over to here because we can partition that out a little bit better, because we can use the calculation for evaporation and transpiration to come up with numbers like 23 of the ocean were lost to evaporation, right? 28 on land was lost to evaporation and transpiration, right? And that asterisk out there means that not only is that a number, but it's a published number based on this paper here, where these guys came up with a method to look at the elastic response of the Earth because of all that weight of that fresh water, which is affecting all the GPS reference stations, right? And it was bending the surface of the Earth, right? And as the water evaporated or moved or whatever, there was a rebound of the Earth's elastic surface, and they were able to measure that. So that measurement comes through. So they were able to say 23, the 28 is from their measurement. The 23 is my measurement based on 1 millimeter per square meter per day of evaporation, which is there's about 6 papers written on that, and they're all agreement with about 1 millimeter per day per square meter is what the evaporation rate is in the ocean. All right, so that's what I used for that. Up there for the 23, they were from this paper, they came up with a number of 12 for the groundwater. So that disappeared into the groundwater in this area. Captured on land and embankments and in levees came out to be 26. And what that left then was, all those numbers say that about 52 cubic kilometers then would come out into the ocean, right? And there's 21 that remained after the evaporation in the ocean. So 52 and 21 are the two numbers that I come up with. It was 73. So 73. And then compare that to what the crews came up with, which was 67 plus or minus 5. So that is what I came up with. And that says that we account for about 92% of the fresh water that should have been on the shelf. We accounted for it in our cruise design. Well, that's, that's kind of like, what? Seriously, you came up with that? Well, it's good to be, good. It's also even better to be lucky. Because it's part of this is, who knew there was going to be a storm like that after our second cruise, right? And that's why we wrote the rapid, because it's like, we just did the cruise here. We have a good shelf survey. We need to go out and measure again. Some of the implications for this, so 73, 67, 6 is the difference here. 52 went from land to the ocean. But if you look at the USGS river gauges for coastal Texas, only 1 cubic kilometer was actually gauged of fresh water. So that means most of that water came over people's lawns and through their house and over ungauged barrier islands, right? So a lot of implication for the modeling of this, like how do you model that? First of all, this is a storm that was not coastal surge inundation. This was the opposite of that. This was raining on the land and then moving out. Galveston Bay, the publications are out. Galveston Bay was the fresh water, the entire volume of Galveston Bay replaced 3 times during this storm. Entire volume. So you talk about impact to the oysters and the other commercial fisheries that are in that bay. They're still trying to recover from that storm. We have a numerical model as well, and that model. So this is, of course, this numerical model doesn't. This is based. So this is Headland's model. So the people that are running it right now, DJ Kobashi, Kristen Thing, Yonggang Liu is who's running it right now. But at the time, this was just the gauge stations along the Texas coast. So it does a good job because it's qualitatively reproduces what we saw with the observation, but quantitatively, it's all off because only 1 cubic kilometer came out that was gauged. So you can see that this star shows where the Flower Garden Banks is, and also shows that it's very, from the model point of view, not much impact. So in the end here, TAB's network and research cruises provided a really nice description of what was going on during and post the storm. The network tracked the movements of that fresh water. We did come up with this conclusion, which was the plume did not get to the Flower Garden Banks. We have lots of reasons for that. And that in the end, 67 cubic kilometers of fresh water was on the shelf, which was 41% of the total rainfall. It was out on the shelf about a month after the storm. So, and just to emphasize, and a lot of people in this room know this, but I want to reiterate to reinforce what you're learning in your class. None of this happens if you don't have a sustainable ocean observatory in place at the time of the event. Right? It's too late to put it out after the event. It's just too late, right? So having a high resolution precipitation satellite that gives me estimates of both on land and on the ocean, right? Having this terrestrial GPS reference data system was just without measure how valuable it was, right? Emphasizes the importance of sustained real-time observations, being adaptive, right? Getting out and doing the work in an adaptive way, and then be lucky. We were lucky. We had the pre-cruise. That's lucky. Take advantage of your luck. Okay, so full stop. I'll talk to you a little bit about now this other experiment that I can't resist talking about. So UGOs, was put in place. So put in place, as you know, and a lot of people know, after Deepwater Horizon, there was a penalty phase. About $500 million went to the National Academy as part to really start the Gulf Research Program, right? And so the advisory board for that was put together in 2016. Is Monty here? Because he was on that board. Tony Knapp was on that board. The consensus report study was published in 2018. Dr. Weisberg and I were on that. And then there was 3 rounds of funding, which was about $40 million to date right now. The goal, and that's the report that's over there, is to advance understanding of blue current dynamics, to improve forecast, and to reduce risk for the energy sector. Right? Those are the stated goals. That little bar at the bottom says OTC. So the OTC, I reported some of this at the Offshore Technology Conference in Houston. It's every year, the first week of May. If you've never been, go. You cannot believe what that's like. It's they fill up the Reliance Stadium. They put giant equipment. They used to put a whole rig inside the Astrodome back in the day. But you have to see it. You can't believe. Wonder where the money is? That's where the money is. It's at OTC. The stuff they have there. We have a roadmap here. In fact, I will bring you here because you are here. And so I'm going to talk a little bit about MASTR. The whole program here starts with stakeholders. If you don't know what people want and need, you don't have a program. Like who is going to sustain this program in 5 years at the end of the program? Right? Because it's not going to be NAS and it's not going to be NOAA. It certainly won't be the National Science Foundation. Right? Who's going to sustain it? Well, it's going to be the stakeholders, people that use it and need it. Right? Talking with them. That feeds into the blue box, which is operational observations and model tools to improve predictions. That feeds down into a pathway for transition to operations, which in the end, how is this going to be maintained as an operational program? Right? And what I'm going to talk about is the mini adaptive sampling test run that was put together because I didn't believe that we were going to be able, Chad, I was not believing that we were going to be able to do this. And I was like, we're going to have that many gliders in the water. We're going to have airplanes. We're going to have floats. We're going to have drifters. How is that all going to work? In 3 different EEZs, including Cuba? How's that going to work? Well, it worked. So 4 gliders, 2 from CSSA, right? So my friends in CSSA put 2 in, Enrique and Miguel. We had Travis and Scott Glenn put 1 glider from Rutgers. We had our team put in 1 glider. All right, so 4 gliders. We had the University of Miami, that's Nick Shea, putting in an Apex. Unfortunately, that Apex never made it into the water. In red here, these are our industry partners. So we had Woods Hole Group providing drifters. We had the Yucatan radar. We had Fugro provide the overflights of the Brocas airplane, right, to provide 100-meter resolution surface currents along the pathway of the airplane. And we had operational models that include the Navy model GOFs. We had the European Union CMEMs. We had the NOAA model RTOPs. Right. We also had access to the industry model from CLS, the TOPS DA, so data assimilative model. We also had, and I will tell you, this was probably the most time-consuming part of this entire endeavor, was to get U.S. State Department permission to do all this work in all of the DEZs. It took us literally 2 years, almost every day working on it. A team of people working. And who was that team? There was more than 60 people working on this. And one of the most satisfying points of my entire career is working on this particular project. So many people all focused on the same goal. Let's get this into the water. Let's see if this can get done. Right. So you can see all the different locations on here, different places, 16 different institutions, 3 different countries, including folks in Cuba. Right. Had that here. And again, I cannot say enough about how cooperative the Mexican consulates were for us. They helped us at every stage of this. That includes, though, we had to put in more than 30 documents that were all translated from English into Spanish. Right, every one of those documents had to be in a format and translated so that people can understand it. And by the way, every time the glider passed into the Cuban EEZ, I had to send an email. I had to send an email to the Cuban military saying, "We're in your water again." Every time it left, we had to send another email. So what did we do? Well, this is what we did. So of course, the boat that we deployed the gliders on was called Black Pearl. Why else? Right? It's out of near Chetumal in Quintana Roo, and it was called the Black Pearl. Bunch of pirates. So here's some of the glider statistics. So we had 4 gliders in the water. They were in the collectively more than about 300 days worth of data that were collected. We got how many profiles is right here. So more than 3,000 went to the GTS, the Global Telecommunication System. That in itself, that was a coup in itself, just to get the Mexican gliders and the US gliders in Cuban water, all reporting to the GTS all at the same time. That was a coup. Distance traveled, more than 6,600 kilometers. Well, let's put that in perspective. That's the radius of the Earth. I'm just saying, there was a lot of data that was collected, a lot of profiles. In fact, it's comparable that since these are 1,000-meter profiles, 1,000 meters times 3,000, that's 3,000 kilometers worth of data that were collected along a range that was the radius of the Earth. And this is showing where all the gliders went, right? So this includes several transects into Cuban water. The EZs are shown here in red. And you can see the different locations as the gliders went around and around and around. And the different gliders here. So RU-38 is the Rutgers glider, Stamo is the Texas A&M glider, and the C gliders that Sesame have are the serial number 625 and 652. And I know that's a little bit dyslexic to say that those numbers are reversed. So this is location showing this. This is an animation over there, and it has some. There is a soundtrack that goes with this, right? So, and some of you might have already heard it, but I'm going to just set it up for a second here. This is going to step through the time frame that starts in January of this year and goes to May of this year. All right, so every hour that's going to change. It's going to show the footprint of the HF radar, which is going to show up there. When this starts, there wasn't a footprint, so it doesn't show it. That cyan color there is the NDVC buoy that's going to show wind, speed, and direction at that buoy location. The gliders are going to be in these colors. Most of the gliders are, I think all the gliders are in triangles, right? Different gliders have different colors associated with them, right? And that's the Success glider 652 showing there. What the vector shows there is the depth average current at that time. Right, so it's the velocity as estimated from the glider trajectory based on a GPS positional change, right? You know what the glider is supposed to be doing in a static ocean, and what they do is they back out that number, and what's remaining is what the depth average current is, right, from 1,000 meters to the surface. Right, you're going to see that there. The green here is the location of where the radar are, and then these magenta triangles are showing where the profiling inverted echo sounders that Scripps put out last fall. They are not in real time. I'm just showing them there to show them, right, that there will be data coming out of them, but right now there is no data that I have seen. I'm hoping to see something.
So what do they do? The Scripps ones.
So yeah, that's so they have a system set up so that they're collecting the bottom time of flight data, and the plan is for them to telemeter that data acoustically to a float at the surface.
Okay, so it's basically a pie, but with telemetry.
Yeah. So, but I'm hoping to see that data.
What happened to Rhode Island?
Yeah, so Rhode Island's, so Randy and Kathy, that data, their systems are up closer to the Mississippi Canyon area. So so they've set up a topographic Rossby wave of Randy up in the northern part of the Gulf of Mexico. So what you're going to see is this evolve, and so okay, so I'm just going to say I'm going to stop talking and enjoy. Two gliders from Success A. You can see the depth average current aligning with the HF radar. Two other gliders go in after that. So now there's four gliders in the water. You can see some flux surface drifters that are being deployed off your frozen mountain. Argo floats come in and out. You can see them come in with their 10-day repeat cycles. Broker's airplane, you can see that it's red. They flash in, flash off because it only takes them a few hours to get around the airplane. One of the gliders got recovered. The first glider had some problems with the sea glider had some problems. This is the first Cuban transect, so this is the Arctic. This Rutgers glider goes all the way across, very close to the coastal water. We had to turn around. We had to get got to turn it around. We're not allowed in there. So this is Stalma. So Stalma's taking that transect across now. It's a Cuban water. Tried pushing it now towards the Caymans, which succeeded. Another glider gets recovered. You can see that the third glider now, this Mexican glider going into Cuban water and then coming out. So we're going to recover the Stamo, Texas A&M glider, and the last glider that's recovered is the Success A glider. And at the end here, you can see that. So that's our glider getting recovered. So it disappears. The last glider that's in here gets recovered. You can applaud. Go ahead. It feels like seriously, we just did that. Like I didn't believe. I literally, didn't believe we could do that. So one of the things that happened organically during this is we got the MIT group involved. Let's see. Oh, come on, no. We got the MIT group organically involved in this because they were saying to us, "What do you guys need? Can you help us? Help you?" We're like, "Well, we meet every Thursday afternoon, so come to our meetings." So they started showing up, and early on they were like just listening, but it became very apparent that if you're going to fly gliders in 4-knot, 5-knot currents, right? Gliders only do 23 centimeters per second. You're going to need help. Like you need some reachability analysis. And so they started producing maps of reachability. So some of us know this GHOST protocol that the Navy has, which is proprietary to the Navy and it provides guidance to glide GHOST. The G in GHOST stands for gliders. I can never remember that acronym. But we don't have access to that actual algorithm, right? So let's come up with our own algorithm that could be publicly available. So what does it do? Well, what happens here is like, if I'm a glider right there, I'm right there. And I have flight characteristics, I know how it can move, right? I know that the glider has physical limitations to it, physical characteristics to it, and how fast it can dive, how fast it can move. Well, what MIT then does, using their machine learning algorithms, they're able to come up with, if I'm a glider there and I have known flight characteristic, where can I be given my numerical model, which is an environmental model, circulation model, and it's an ensemble model, 8-member ensemble model. Where can I get to in 12 hours? And so the first concentric circle here is 12 hours. Where can I get to in 24 hours? That's the next concentric circle, right? And so on. with that. So where can I get to? And this is all done, really, it was done organically. It was like, that would be really cool to have. We want more of that. And it became too that since they have an ensemble model, that the colored background here is the variance of the ensemble, right? Which is showing where the uncertainty is the great. So white here is where the uncertainty is the greatest. And so using reachability plus uncertainty, you can start saying things like, you can make my model better if you can get a glider into the light. Can I get there? Can I get there in 12 hours? Can I get that? And so this is just a snapshot. One, you can go to this site here. They have a lot more information there about this. Right? This is the MC's MIT. This is Pierre Vermassu, his group working on this. But it's saying things like, well, if you get your glider here, to make my model better. And I'm like, I can't get my glider there in 2 or 3 days. Can't get there because the reachability won't allow me to get there. But they started using this. All the pilots started as part of this project because they're in a 4-knot current, right, with the Yucatan. How am I going to get across that current, right? So use this, right? And they used it, and the results kind of speak for themselves. They were able to stem that current. We were never swept to the north. We never had to ask Nick Shea to go out and waders at Key West and go rescue our glider. We never had to do that. He would do that. I know he would do that for us. Never had to do that. So we started making graphics of this, and I know I'm at the end of my time here, but let me just show you this. Started making graphics. Let's say that. We started making graphics like 3-dimensional representation of the different so surface height. Yeah, see surface height anomaly is showing up on the top here. That's the color sheet. The glider showing the different salinity that's underneath all of this. So these are all different gliders. You can see the location of where it is on the surface. These are 1,000-meter dives. It's showing the yellow here is the subtropical underwater coming in through the Caribbean, right? So it's the salinity high there that's being shown. Once we started making maps of this, it started becoming obvious to us that there was an issue with the numerical models. I'll show you that issue. Before the glider data started getting assimilated, this is the red here is the NOAA model. This is the vertical structure of salinity in this location, at this location in the Yucatan, before the glider data really started, right? And green here is the Navy model. And the purple here is the CMS model, and blue here is the observations. And what this is saying here is that the models are too fresh and too cold, which means they're not spicy enough. The spice is not right, which is ironic because we're in Mexico and Cuba, right? That should be more spicy, right? My friends at CFSA were saying to me, you shouldn't play this play the Bumblebee. You should play some salsa music. I said, I will put that under advisement and I'll see if there is a public domain salsa that I can use for that. If that's what things look like before before the data from the gliders are getting assimilated, this is showing after the data assimilation. So all of a sudden you see things starting to line up much, much better because the data now from the gliders making the models better. It's getting that subtropical underwater, the salinity maximum better. Which leads to the question, why is it so wrong in the first place? Like, what's wrong with the climatology? Because they're all starting from some kind of climatology. So, but I'll tell you right now, after those gliders came out of the water, they spent 3 months in the water, all the models have gone back to what it was before. And Bob Weisberg told me a long, long time ago, if you keep doing things the same way, you're never going to get a solution. Keep doing things the same way, you're not going to get a solution. You need to get this right. You need to get this hydrography right? Because it talks about how much volume is going through that channel, how much heat is going through that channel, how much salt is going through that channel. If you don't get that right, you're going to get a lot of things. So, bottom line. And then demonstration, we did it. Right? From diplomacy, which took years, to the logistics, to the collection, to dissemination, to ingestion in the models, we did it. how do we assess success, right? So data delivery of all these different platforms, right? Deployed simultaneously in this region. And then ingesting that information into all these models for data assimilation. Right? A lot of models don't do assimilation, right? The ones looks like right now, based on what we're seeing here, get better. Right now, we're looking at doing the assessment of that assimilation and how did that, what was the quantification of that impact? Working on that now. Unexpected success. Those operational tools like the reachability. I didn't expect that when we started. It just happened. I didn't talk at all about the influence of Aerosmith Bank, and it's not the band Aerosmith. It's the like on the edge. Walk this way. It's not that. The arrow, like an arrow, like arrow on the dynamics, and it's something that's so small that most of the models do not capture. I don't know if your model captures it. Aerosmith Bank. It's north and east of Coast Mountain. Right. It's only 20 meters deep there, but the radar data is showing that there's a quantum jump between either the Yucatan currents to the east or to the west. And that's going to influence the dynamics. And then the last thing here, unexpected simulation revelations, the Caribbean hydrography and the position of the Yucatan current core. So my last slides here. So there's just a lot of team members on this. So I already showed you the team for MASTR. This is the Harvey team. If you like the color bars, CM Ocean, right? Kristen thing, and yeah, I know I'm a co-author. I give a citation every time you use it, but they are awesome color bars. So this is my next. So our mantra at GERD is collect data, not dust. Every time that glider or that buoy or that whatever is in my lab, it's not collecting data. It's not making any money for it. Like it's just collecting dust. Collect that data. And then lastly here, this last picture. Give me that picture. I said before the buoy heroes. So this is the scene on the back deck of the Brooks McCall on 26th of August, when they just turned the ship into the seas, into the wind, and just hung out there for a couple of weeks. This was the first time that Adam, was one of our techs, was able to stand on the boat. I took a picture out the back hatch and just raging seas going. So anyway, so and thank you so much thank you for indulging me a couple more extra minutes. But thank you so much for having me here. I've really enjoyed my stay and seeing a lot of my friends. And I can answer questions if you have them. If you want to stay, it's up to you. Thank you.